Yeah, thank you for the warm welcome. Then, before I start, I want to go back some years. Once I came home, and there was my flatmate, and he was quite nervous. He was walking up and down and really tensely, and I didn't know what happened. And I was thinking, he was really a nerd. I was thinking maybe there was the release of a new Marvel crossover, James Bond versus Richard Ironheart, or I don't know, some shit like that. But no, it wasn't. Then I thought maybe it's his girlfriend. He has some argument with her, but he didn't have a girlfriend. So it was something else. And the reason why he was so upset was PlayStation 5 couldn't be delivered. And if you remember, a few years ago, there was this supply chain problems in semiconductors, and one reason of that was this ship blocking the Suez Canal. Yes, and then the reason was because of chips couldn't be delivered. But maybe you are not so interested in these chips to eat, so I've prepared something. So wait a moment. You see, I'm well prepared with this scientific instruments. So, who of you has ever seen that? Yes, a few of you. Nice. So these are semiconductors, and you see this is kind of silicon. It's a single crystal, quite huge, and every single atom is at the right position. It's a perfect shape, and we have really tiny structures, and it's not that easy to fabricate. And so that's kind of the reason why a ship and a Suez Channel can block our supply chain of semiconductors, because it's so complicated to fabricate them that we need the whole world and on every continent some fabrication facilities. But to understand why they are so interesting and important for our society, I want to explain you some details about them. So why semiconductors are so interesting is, on the one hand, they have band structure. So they have bands, and maybe you think about that, but it's something else. So bands in semiconductors is kind of where electrons can live, charges can live, and we want to control these charges, because these charges can contain information, and with this information we can do integrated circuits for computers to treat information. Imagine a band like this bottle, and when this bottle is completely filled, imagine it would be completely filled, maybe we can fill it like that. So you see, there's not much moving, but if I put a little bit of air in, so the water can move, then you see it's a bit better to be moved. And on the other hand, we can have bands that are just half filled, and you see it's really easy to move the water. And then there are maybe bands which are not at all filled. Imagine it's empty. Nothing happens. That's what's happening in solid state. So what you see here, some details, don't bother. We have insulators. In insulators, there's one band which is completely filled, nothing can happen. And the other band is completely empty, nothing can happen. And at metals, there's one band which is really filled a little bit, and then everything can move like it wants. You can shake it. Electrons can move, and that's the reason why you usually use metals, for example, for your plug at home when you plug something in your electricity stuff. And the nice thing with semiconductors, it's in between. So it's close to be a little bit empty, and it's close to be a little bit filled, and that's why we can easily control how much it is filled or how much it is empty, and so we can control how easy electrons can move or charges can move, and information can be spread or treated in our semiconductors, and then we can compute with it and do all these nice things we can do with semiconductors. And I think you know all these things. So this we have in the institute, integrated circuits, LEDs, for example, we have a lot of them here. Yes, some tools, Game Boy, and of course, maybe you know this. Who of you knows this still? Yes. But there's one backside. So back in the days when this stuff was developed, do you know who financed it? Does anybody know who financed the development of semiconductors, integrated circuits? Yes, the Minuteman program from the US Army. So this is a nuclear intercontinental rocket which is controlled by an integrated circuit. And because US Army paid for that a lot of money to the company Fairchild, this company also had enough money and enough resources to then later build all these markets for consumer products. So always you see this, you know, we only have to tolerate it because there are intercontinental weapons. Then now you maybe ask, the title was nano-drums, and up to now there are no drums. So here are the drums. Who knows this guy? Some of the, yeah, nice. I even heard the name, Richard Feynman, Nobel Prize winner. And of course, as Nobel Prize winner, you have to play instruments. And so now is the question, what have drums and semiconductors have in common? Yes, of course, we can just build semiconductor drums. So what you see here is silicon nitride, and so this is kind of semiconductor, and there are holes, these circles are holes, and on top of that we put really tiny and really thin layers of material, and there is the hole, the material can vibrate and move, and this is a drum. And we can do this also in silicon oxide, what you see here, and here it also can vibrate, and we have, like at a real drum, we have resonances, and we can listen to the sound. And to develop this and to really fabricate these really thin layers of material, there were some people who won a Nobel Prize with a groundbreaking scientific method. And I want to show you this very complicated apparatus to do it. Yes, it was kind of scotch. And so you take the material, take the scotch, and then you transfer it to your holes, for example, or to the structure you want to use. And now you may ask, okay, we have the hole, we can transfer this material to the hole, but why does it work? Why do we get such a thin layer, like a real drum, a membrane, which is huge and large in one direction, and the other is really thin, like the membrane of a drum? And there I have the last part of my title. Who guesses what? A croissant. Because like the croissant, it's huge, but you have always this thin stuff, which is really thin, but large, and it tastes good. This is so-called van der Waals materials, or 2D materials, where in one direction, or in two directions, in this and in this, there are really strong chemical bonds which keep the material together. But in the other direction, it's really weak. And this is why we can take the scotch here, take it apart, and transfer it to a hole, and we have a drum, like at the croissant. Now you may ask, okay, where's the quantum? Here's the quantum. Here we have the drums, the mechanical drums. Then we want to put them in an optical cavity, which is kind of two mirrors. We put it in, then we couple it. You see here the Hamiltonian. I think you're familiar with Hamiltonians and harmonical oscillators. I think it's quite trivial. And then we want to couple it to atomistic defects into the material and do hybrid quantum systems. So I hope the ones of you who were thinking about studying physics because the talk was so nice, now I hope you may decide different. But for the others, we also have nano harps, and some others, not us, do nano guitars, and of course Richard Feynman does the drums. So thank you for your attention.
Lukas Schleicher from MCQST.